A moving coil galvanometer is used to detect the direction of current in electric circuits. It is also used to measure small magnitudes of currents and voltages in electric circuits. The moving coil galvanometer works on the principle that when a current-carrying coil is placed in a uniform external magnetic field, it experiences a torque. Let us discuss this in detail. Before discussing the work of a moving coil galvanometer, let us have a look at its essential parts. The moving coil galvanometer consists of circular-shaped magnetic poles, which create a uniform radial magnetic field. It also consists of a current-carrying coil of many turns wounded in a rectangular shape over a soft iron core. The soft iron core increases the strength of the uniform radial magnetic field. In the radial magnetic field, the plane of the coil is always parallel to the direction of the magnetic field for any orientation. Hence, the angle between the plane of the coil and the direction of the magnetic field is always 0. And the angle between the axis of the coil and the magnetic field, theta, is always 90 degrees. A spring, denoted as SP, is connected to the axis of the soft iron core. On close observation, we find that one end of the spring is connected to the axis of the soft iron core, and the other is connected to a rigid support. A pointer is connected to the axis of the soft iron core. This pointer moves over a circular scale. Now, let us discuss the working of the moving coil galvanometer. When an electric source is connected to the terminals of the rectangular coil, a torque is produced. That is, when a current passes through the rectangular coil, two equal and opposite forces acting on either side of the coil produce a couple. In our present context, we refer to this couple as the torque. As you learnt earlier, the torque acting on the coil τ is equal to BIAN sin theta, where theta is the angle between the axis of the coil and the magnetic field. Here, theta is 90 degrees. Thus, sin 90 is 1, and we have the deflecting torque acting on the coil tau equal to BIAN, where B is the strength of the uniform magnetic field, A is the area of the current-carrying coil, N is the number of turns in the coil, and I is the current passing through the coil. Let this be equation 1. This deflecting torque in the coil develops an equal restoring torque in the spring in the direction opposite to that of the deflecting torque. Hence, these two torques are balanced. The restoring torque produced in the spring is tau is equal to k phi, where phi is the deflection shown by the pointer and k is the torsional spring constant, the torque per unit angle. Let this be equation 2. Equating the expressions 1 and 2, and on simplification, we get phi is equal to BAN by K into I. Let this be equation 3. The value of BAN by K is constant for any given galvanometer. Hence, phi is directly proportional to I. That is, if the current passing through the coil increases, the deflection of the pointer also increases. By passing a known value of current and measuring the corresponding deflection in the coil, phi is found. From this, the deflection per unit current is calculated, and then the circular scale above which the pointer moves is graduated. This is known as calibration of the galvanometer. The ratio phi to I gives the deflection per unit angle, which is defined to be the current sensitivity. From equation 3, phi is equal to BAN by K into I. Hence, the current sensitivity phi by I is equal to BAN by K. The current sensitivity of the galvanometer can be increased by increasing the number of turns in the coil. It can also be increased by increasing the area of the coil or by increasing the strength of the magnetic field. As we discussed in the beginning of the module, a moving coil galvanometer has some applications. Let us begin our discussion with its applications in the detection of the direction of current in a given circuit. Consider a Wheatstone bridge circuit, which we learnt earlier. In this circuit, a galvanometer is used to detect the direction of current in the bridge part of the circuit. In this arrangement, the type of the galvanometer used has 0 reading in the center of the scale. The readings on the right side of 0 are considered positive, and the readings on the left side of the 0 are considered negative. When there is no current passing through the galvanometer, it shows the reading 0. Depending on the direction of current in the circuit, the galvanometer deflects either towards the right or towards the left. For example, consider that 1 microampere current is allowed to pass through the central part of the arrangement. Then, the pointer deflects towards the right side of the 0 on the scale. If the current passes from top to bottom, the pointer deflects towards the left of 0 on the scale if the current passes in the reverse direction. Galvanometer is also used to measure small magnitudes of currents in a given circuit by connecting it in series. For simplicity, let us consider a circuit diagram where the galvanometer is denoted as G. As the galvanometer consists of the long coil, it has some resistance. We refer to this as the resistance of the galvanometer, denoted by Rg. In contrast to an ammeter, which measures even current of high magnitudes, a galvanometer is used to measure small amounts of current such as in microampere. Why can't we use a galvanometer as an ammeter? There are 2 reasons. First is due to the fact that the galvanometer is a highly sensitive device. The full-scale reading on the galvanometer is in the order of microampere only. And the second is, to measure the currents in electric circuits, the galvanometer has to be connected in series. Due to the resistance of the galvanometer, it can affect the value of current in the circuit when connected. This difficulty can be overcome by connecting a small resistance, Rs, in parallel to the galvanometer. This small resistance is called as the shunt resistance. When a shunt resistance is connected in parallel to the galvanometer, most of the current passes through this shunt. Thus, the change in current in the circuit is negligible. Thus, a galvanometer can be converted into an ammeter by connecting a shunt resistance in parallel to the galvanometer. The effective resistance of the galvanometer and the shunt resistance is equal to RG/RS by RG plus RS. But the galvanometer resistance is a lot higher than the shunt resistance. That is, RG is very large as compared to RS. In that case, RG plus RS becomes approximately equal to RG. Hence, the effective resistance becomes approximately equal to RS. The effective resistance of the galvanometer and the shunt resistance is in series with the resistance of the rest of the circuit. Let the resistance of the rest of the circuit be denoted as RC. Thus, the effective resistance of the total circuit is equal to RS plus RC. But the value of the shunt resistance is a lot lesser than the resistance of the rest of the circuit. That is, RS is extremely small as compared to RC. Thus, the effective resistance of the total circuit is approximately equal to RC. That is, the resistance of the measuring device in the circuit is negligible. Thus, the galvanometer can be converted into an ammeter by connecting a shunt resistance in parallel. And the scale of this ammeter is calibrated and graduated according to the current sensitivity. The galvanometer can also be used to measure the voltage across any given part of the circuit by connecting the galvanometer in parallel with the given part of the circuit. When the galvanometer is connected in parallel, the total current in the circuit divides across the part of the circuit and across the galvanometer. The galvanometer must draw a very small current from the circuit. Otherwise, the original value of the current in the circuit will be altered. In general, the alteration in current due to the measuring device in the circuit must be negligible. It should be less than 1% of the original value. To reduce the alteration in current due to the galvanometer, a large resistance is connected in series to the galvanometer. Let the large resistance be R. R being very much greater than Rg, the current passing through the galvanometer is minimized to less than 1%. Thus, the galvanometer can be converted into voltmeter by connecting a large resistance in series with the galvanometer. The effective resistance of the galvanometer and the large resistance is equal to R plus Rg. As the resistance R is very much greater than the resistance of the galvanometer, Rg, the effective resistance is approximately equal to R. Hence, a galvanometer can be converted into a voltmeter by connecting a large resistance in series. The voltmeter is calibrated and graduated on the scale according to the voltage sensitivity. Voltage sensitivity of the voltmeter is defined as the deflection per unit voltage, denoted as phi by V. From equation 3, phi is equal to BAN by K into I. Divide with voltage V on both sides Phi by V is equal to BAN by K into I by V. From Ohm's law, V is equal to IR. Then, I by V is equal to 1 by R. Then, the voltage sensitivity, Phi by V, is equal to BAN by K into 1 by R. In the case of the conversion of a galvanometer into voltmeter, an increase in the current sensitivity, which is the ratio of Phi to I, does not increase the voltage sensitivity. Let us look at this in detail. Suppose the number of turns in the coil of a galvanometer is doubled, that is, N becomes 2N. By substituting 2N in place of N and on simplification, we get the new value of Phi by I as 2 Phi by I. That is, the current sensitivity is doubled. We know that the resistance of a wire is directly proportional to its length. As the number of turns in the galvanometer coil is doubled, length of the wire in the coil is also doubled. Thus, N becomes 2N, which implies L becomes 2L. Thus, the effective resistance R becomes 2R. By substituting 2N and 2R in place of N and R respectively, we observe that the new value of Phi by V remains the same. That is, by increasing the number of turns, current sensitivity can be increased, but the voltage sensitivity remains the same.